तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We will move on to lecture number 47 on our series on mechanical measurements. In the last lecture, we were discussing about vibration measurement, and we were looking at a second order system which basically represents a vibration measuring device, and we were trying to understand the basic principles. And so what we will do in the present lecture is to recapitulate what we did in the last lecture and carry on from there. So we will discuss the principles of operation of a vibration measuring system. Then we will subsequently, can we have the slide please? Then we will look at the two examples 53 and 54, which will deal with the application of these principles, and then I will discuss one kind of accelerometer called the piezoelectric accelerometer. It is very common and used commonly in practice. Subsequently, we will look at a laser Doppler accelerometer, which is a thing which is more recent in origin, and we will look at some of the principles involved in these. So, if we go back to the slide, the equations which we had derived in the last lecture, they were labeled as 1 and 2 here. So, the amplitude response of a second order system, which consists of a mass with a spring, the movement is against the spring, and there is a damping. The damping can be due to viscous effect, and the response is written in terms of the response to a sinusoidal input. That means that the vibration is the vibration which is imposed on the system is having a frequency of omega 1, and the natural frequency of the system is omega n. So, what we are talking about is the response of the system to the input. Input has an amplitude x naught, and that is given by expression number 1. So, it is given by omega 1 by omega n whole squared divided by square root of 1 minus omega 1 by omega n whole squared, plus there is a 2 into c by cc. This is the ratio of the viscous damping to that in the case of critically damped second order system multiplied by omega by omega n whole squared. And there is also an accompanying phase lag which is given by the tan inverse 2 c by cc omega 1 by omega n divided by 1 minus omega 1 by omega n whole squared. Similarly, we can also look at the acceleration response, for which we know that the acceleration due to the variation of x1 in a sinusoidal or in a periodic fashion is given by this formula minus x naught omega 1 squared times cos omega 1 t. So, equation 1 can be modified to give the acceleration response as given by k equal to 1 over that omega squared goes off 1 over square root of 1 minus omega 1 by omega n whole squared plus 2 c by c omega 1 by omega n whole squared. So, these are the three equations which were derived, and these are the basic things which are going to discuss to govern the behavior of an accelerometer, and we will look at some of these by looking at the response in a plotted in a particular way. So, first we look at the amplitude ratio, which is given by x2 minus x1 divided by x naught, plotted as a function of frequency response, frequency ratio omega by omega n, and what we have done is we have given the response as a function of or for different values of the damping parameter. So, if you do not have any damping at all, at omega 1 equal to omega n, that is the input frequency equal to the natural frequency system, in principle the amplitude is going to become infinite. Of course, in practice there is no system with 0 damping, and therefore, this is only an idealization. In other words, if the damping is very small, the amplitude can become very large, that is what it means, at the condition omega by omega n equal to 1. As the damping ratio is increased, so I have plotted for 0.2, 0.4, 0.6, 0.8 and 1, you see that the amplitude becomes more manageable. The amplitude, for example, if the value of the damping ratio C by Cc is greater than 0.6, the response is never greater than 1, it is always below 1. That means that the amplitude ratio is reduced to a value less than or equal to 1. You also will notice that the amplitude ratio varies quite significantly for omega less than omega n, and actually it grows in size, and for large values of omega by omega 1, that is for large values of the frequency input frequency compared to the natural frequency system, the value more or less tends to 1, at least it is close to 1 here. So, we can easily see that. In the next sketch I have actually done that. If you take the look at a particular case with C by Cc equal to 0.7, the damping ratio equal to 0.7, you see that the amplitude ratio, if the value is more than about 2, omega by omega n greater than about 2, you see that it is very close to 1. So, we say that any value omega by omega n less greater than 2 is a useful range for measurement of the amplitude of the vibration. So, this is for the measurement of the amplitude of the vibration. The second point I would like to mention here is that if you remember in the previous lecture, we indicated that we can limit the amplitude of the vibrometer or vibration sensing device by putting stops. So, if I put a stop such that it is not more than, let us say 1.25, then you see that for different damping ratios you see the kind of behavior you are going to get. For example, if I do the experiment with C by Cc equal to 0.4, it will go up to this, and when it hits the stop it is not going to change. So, it is going to stay constant, and then it is going to come back like that. So, one way of preventing the runaway of the transducer is to put stops, so that the amplitude is limited to a certain value. In this case I have taken 1.25, you can put it even less than 1 or more than 1 as the case may be. That will prevent the vibration sensing device from executing too large an amplitude and probably wrecking the sensor itself. So, the thing we notice is that for measuring the amplitude of the vibration, the useful range of the instrument is such that we must have the input frequency greater than about 2 times the natural frequency of the system. So, you can immediately see that if we are going to measure the amplitude of vibration of a system, let us say varying at a fairly low frequency, if the low frequency, then omega n must be even lower than that. For example, if I have a frequency of let us say 1 hertz, this factor 2 here means that the natural frequency must be even less than that, half a hertz, half of the impressed frequency. Therefore, your natural frequency must be chosen even smaller than that. We will discuss when we take up an example, it will become clear to you as to what we are talking about. The second relation we had was with respect to the phase relationship, and the phase angle in degrees is plotted here again with respect to frequency ratio. omega by omega n, and you see here that the phase changes from 0. That will be, that means that when the frequency ratio is very very small, the movement of the, or the motion of the transducer is in phase with the input disturbance. But as you see, when the frequency becomes almost equal to natural frequency, actually the phase lag is there of 90 degrees. That is the phase angle of 90 degrees difference between input and the output. And for omega by omega n greater than 1, you see that the phase is actually becoming larger phase difference, and in the limit as omega by omega n tends to infinity, the phase difference goes to 180 degrees. So, this is very important, the phase relationship is very important. So, how does the phase relationship become important? We will be actually taking a look at a particular example, which will make it clear as to what the implication of this is. For example, if I look at the special case of C by C is equal to 0.7, that means the damping ratio is 0.7 times the critical damping ratio, then you see that the frequency versus phase shows this kind of a change, and you see that for a value greater than about 4, the frequency ratio greater than about 4, you see that there is almost a linear phase shift with respect to frequency. This is a very important observation, as it will become clear to you when we take up the example. So, the higher the frequency, higher the phase shift, and the phase shift is linearly varying with respect to frequency. This is another second observation we are going to make. So, how these are going to be useful in practice, we will try to look at a little later. The third one is the acceleration response factor k, which is the expression number 3 which I gave on the board. What I have done is I have plotted the acceleration response factor k versus the frequency ratio, but I have used a logarithmic scale on the x axis, so that the figure looks slightly different from what it was earlier, and you will see the important thing here. The acceleration response is almost 100% or close to 1 for omega by omega n, much less than 1. Okay, this is very important. If the impressed frequency is much less than the natural frequency system, the acceleration response is much better. If you remember previously what we discussed, the amplitude response is better, exactly the opposite. Omega by omega n must be larger than 2 or so, what we saw in that case. Therefore, omega much greater than omega n, you have a good amplitude response, and omega by omega very small compared to omega n, you have a better acceleration response. That is, if we are interested in measuring the acceleration due to the vibratory motion, we would have to choose the natural frequency of the transducer to be much larger than the actual frequency at which we are going to measure the acceleration. This is the major thing which comes out from this particular theoretical analysis. So, with this background, let us look at two cases, so that we understand what we are talking about. I will just show the details about the example here, and then we will work it out by writing down the solution. So, what we have here is a big seismic instrument. Seismic instrument is used in measuring mostly the earthquake forces generated during earthquake. It is constructed with a mass of 100 kilogram, fairly large mass. C by Cc has been adjusted to 0.7 by suitable means, and we have a spring constant equal to 5000 newtons per meter, fairly strong spring with a large spring constant of 5000 newtons per meter. So, we want to calculate the value of linear acceleration that would produce a displacement of 5 millimeter on the instrument. That is the part A. Part B, we want to find out what is the frequency ratio omega by omega n, such that the displacement ratio is 0.99. And the thirdly, we would like to find out the useful frequency of operation of this system as an accelerometer. So, three parts of the question are given here. So, what we will do is we will try to work it out by calculating the various things. All it requires is the use of the equations which we already derived. Therefore, nothing new, nothing more than that is required. So, what we will do is we will just find out how to go about. So, we are given in the example 53 the displacement is given 5 millimeters, which is 0.005 meter, and we know that the spring constant of the system is given as 5000 newtons per meter, and the mass or the seismic mass is 100 kilograms. So, if the system is subject to a linear acceleration, we would like to find out what will be the response. So, this is the response due to an imposed acceleration A, let us say. So, it is a very simple thing to find out. The acceleration is nothing but mass times acceleration is equal to the force, and force is proportional is equal to k into delta x, and therefore, all I have to do is to obtain the acceleration as a ratio of force to the mass, and the force itself is given by k into delta x divided by m, very straightforward. This will be 5000 into 0.005 divided by 100 kilogram, that gives you a value of 0.25 meter per second square. So, a linear acceleration of this mass by 0.25 meter per second squared will give rise to a displacement of 0.005 or 5 millimeters, a very sluggish system, as we will see in a moment from now. So, this is the part A of the answer. The part B, what we want to do is to find out the value of omega by omega n. What is omega by omega n such that the amplitude response. The reason why I am working out this example is because it is going to actually tell us about the principles involved in acceleration measurement or in vibration measurement. So, amplitude response is 0.99, 99%. Of course, if the acceleration is linear, that means it is a constant value, as in this case linear acceleration means the accelerometer is simply accelerated in a particular direction with a constant acceleration, that is, there is no periodicity, it is a constant value. So, when you have a constant value for the acceleration, it gives you a constant amplitude output, and it is the same as the actual amplitude. Now, once we start varying it sinusoidally, you see that the response becomes less than 1. It will not be equal to 1, it will be less than 1, and we want to find out when it becomes 0.99. Assuming that up to about 0.99, we can use the instrument as a treating it as a useful range. So, for that, very straightforward, all I have to do is to use the expression number 1 which we had earlier. So, I will say amplitude ratio is equal to 0.99. I will consider omega by omega n, I will write it as y, so that it is easier to write down the expression. That becomes y squared divided by square root of 1 minus y squared whole squared plus 2 into c by c. C by c c is equal to 0.7. We are going to assume c by c c equal to 0.7. So, that becomes 1.4. Then again y squared whole raised to the power 1.5. So, we have to actually solve for the y. Actually, we have to solve for y, and it is very simple. we can square both the sides and then simplify it. So, if I do that, put y squared equal to z, then the above expression will become, you can actually work it out and show this result. Above expression simplifies to the following quadratic equation. So, I will just directly give you the quadratic equation, which will be in z 0.0203 z squared plus 0.04 z minus 1 equal to 0. That is the equation I am going to get. So, this has got two roots, one root will not make sense, one root will probably make sense. So, the root which makes sense is z is equal to 6.1022, z equal to 6.1022, but z itself is equal to y squared. So, we can immediately say that y equal to square root of z is equal to square root of 6.1022, that will give you 2.47. While we were discussing the graph, I said that above a value of omega y omega n roughly equal to 2, it is good as a say sensor of amplitude, but here we see that the 2.47 is the proper value to take. So, if you have a omega y 1 omega n greater than 2.47, the amplitude will be faithfully recorded. What does it mean? Omega n, if we calculate for this system, we can do that. It is simply given by square root of k by m, which will be square root of 5000 divided by 100 kilograms. This is your natural frequency, is about 7.07 hertz. So, this 2.47 means it corresponds to, we will see that, therefore, omega should be greater than 2.47 times 7.07, this will be equal to 17.5 hertz. That is the answer to the second part of the question. The third part of the question, or C part C, wants to look at the acceleration response. Again I am looking at the acceleration response being equal to 0.9 as the limiting value for the utility of the sensor. Response is 0.9. So, again I go back to expression number 3, which was defined, which was given earlier. This is the starting point, and so I will put again equal to 0.99. So, in this case again I use the same symbol, y is equal to omega by omega n. This becomes this expression, 1 minus y squared whole squared plus 1.96, that 1.4 whole squared is 1.96 whole squared and the square root of. So, again I will be able to simplify this expression, and I will leave it as an exercise for you to do, and we should be able to get the following equation. The equation will be, this leads to z squared minus 0.04 z minus 0.203 equal to 0. So, you see that we have a different equation this time. We can actually compare this equation with what we had earlier. You see that the earlier equation was 0.0203 was here, 0.04 and 1, and you see that the numbers have somewhat interchanged. 0.0203 has gone to this place, and the coefficient has become 1 for z. This equation has a solution given by 0.1639 is the solution to this problem. So, that means Z is small. That is exactly what we mentioned earlier, that for small values of omega n, the response to acceleration is better, and for large values of omega n, the response to amplitude is better. That is what we said earlier, and so it is corroborated by this particular discussion. So, Z is 0.1639. This corresponds to y equal to omega by omega n equal to square root of this number. This will be 0.405, and if you multiply by the value of frequency, if you remember what we did earlier, omega n we have already found out. So, we can find out what is the value of omega is. This comes to about 0.105 hertz. Maybe we have made a small mistake. Let me go back, and we should have a value of 2 pi in this formula. Omega n is equal to 2 pi root k by m. So, I think we can make that change. So, let us just look at this. Omega will come out to be 0.105 hertz, which is the value of the omega below which. So, omega should be less than 0.105. That is important. So, very small omegas only it will respond. So, if we look at a typical earthquake, the period of the waves is something like tenths of a second, is 10 seconds to about a few minutes. The waves generated by the earthquake have periods in this particular range, 10 seconds to about a few minutes, and if you calculate the corresponding frequency 2 pi by the period. So, if I take 10 seconds, 2 pi divided by, suppose I take 1 minute, it becomes 60 seconds. This will be so many radians per second, and that comes to about 0.105 hertz. I think this the above result was not correct. This comes to, I will correct this. This comes to about 2.86 hertz. 2.86. And you see here that if you have 1 minute as the period of the earthquake generated wave, you get a very fairly low input frequency, and the accelerometer will certainly respond to this very well. So, the accelerometer will respond very well. So, an accelerometer must have a large mass and a large spring constant, as in this case, and it must have a natural frequency which is much larger than the frequency which is going to be measured, and that is what we have seen in this example. So, the next example let us look at. If you remember, I talked about the linearity of the phase difference. So, if you remember, I said linear phase relationship for large omega or large omega by omega n. So, if you recall, we had something like this is the phase versus omega by omega n. It looked like this, it was almost linear here. So, what is the consequence of this? Let us look at the consequence of this. Suppose we have the following problem. The vibration measuring instrument is being used to measure the vibration of a machine, vibrating according to the relationship which is given. X is made up of two components. That means, an input vibration is made up of two components, one given by 0.007 cos 2 pi t, where it is all in meters. So, 0.007 means 7 millimeters is the amplitude of this particular component, cos 2 pi t, this is the first wave or the first component, because if you remember from your mathematics background, you will see that any periodic wave can be made up of a set of sinusoidals or cosinusoidals by using the Fourier series concept. So, this is nothing but this particular wave is made only of two components with significant energy, and others are not important. So, the second component is 0.0015, this is 1.5 millimeter amplitude, but with a higher frequency of cos 7 pi t. So, I have cos 2 pi t cos. So, two different frequency components are present in the input. So, what we would like to know is the vibration instrument has an undamped natural frequency of 0.4 hertz and a damping ratio equal to 0.7. We would like to find out whether the response of the vibration measuring instrument will be faithful to the input. That means, two things we can say. If it is faithful, the amplitude will be more or less the same as the amplitudes which are given here, and secondly, both these waves must be combined without any distortion. So, we will look at the consequence of this particular wave being we will look at the consequence in terms of the linear phase relationship for large omega by omega. So, what we can do is we can treat the input as two separate components and find out what is the response of the instrument to these two components, and then we will add the two responses, and that should be the response of the instrument. Okay. So, the natural frequency is the vibration of the instrument is given by omega n is equal to 2 pi times the frequency. Frequency is given as 0.4 hertz. So, this becomes 2 pi into 0.4. This will be so many radians per second, or it is equal to 0.8 pi. So, for the first part of the input, it is given by 0.005 cos 2 pi t, that is the input. So, omega 1 is equal to 2 pi, and this is omega n. So, all I have to do is to substitute these values into the expression for amplitude ratio, which we also had in the previous example. So, amplitude ratio for this part of input, all I have to do is to substitute omega by omega n into that formula. So, it will be y 1 squared, assuming divided by square root of 1 minus y 1 squared whole squared plus 1.4 y 1 squared under square root of. So, y 1 is nothing but omega 1 by omega n, that will be 0.8 that that will be given by that will be omega 1 is 2 pi divided by 0.8 pi. That ratio is 2.5. So, I have to put y 1 equal to 2.5 here and work out the value of this, and it comes to 0.9905. So, it is better than 99%. So, the amplitude I can easily calculate 0.9905 into 0.005. So, that is the amplitude response. But let me also look at the phase response. Phase is given by phi 1 is equal to tan inverse 2 into C by C n is 0.7 into ratio is 2.5 is the ratio of omega by omega n divided by 1 minus 2.5 squared under square root of. This gives you a value of 146.31 degrees, or in terms of radius it gives you 2.554 radians. So, we have worked out for the first part of the input. The second part of the input has a higher frequency, and we know omega 2 equal to 7 pi, and therefore, if you take omega 2 by omega n, we call it y 2, it will be 7 pi divided by 0.8 pi. This will give you 8.75. So, for this value of y 2, I can again work out, and we will see that the amplitude response is almost unity. So, amplitude ratio for this component is equal to 1 with up to 4 decimal places, and we will also find out what is the phase for this case. Phi 2 will be again the same formula, but using the 2 point into 0.7 into 8.75 divided by I think the square root is not there. Let me just so please make a correction. It is 2.5 whole squared, square root is not there. And in fact, what I should have done is I should have put a negative value here, because there is phase lag. I am just showing the magnitude. Otherwise, if it is somewhat confusing, you can put that value also. So, the value is 2.2 into 0.7 to 8.75 by this one. This will give you a value of, let me just see, the value of this phi 2 will be 2.981. So, we have the amplitude ratio for the first case is 0.9905, for the second wave is 1. Therefore, there is very small amount of distortion, because the first part is going to be 1% less than the input amplitude. To that extent, there is a small impact on the value of the. So, amplitude wise, amplitude response is more or less faithful. That means very small change in the first component, the second component is more or less preserved. However, if I look at the phase relationship, the output of the output phase of the first component is different from the output phase of the second component. But let us look at this. Now, we can write the output in the following form. It will be 0.9905 into 0.005 cosine 2 pi into t, this is the input wave, there is a phase lag of 2.554 for the first component, plus 1 into 0.0015 into cosine 7 pi t minus 2.981. So, let me just briefly look at what should be happening. If the response to phase response should be preserved, if the shape of the output must follow the shape of the input wave, the following should hold. Suppose I have a cos omega t A1, let me just suppose I have the input A1 cos omega t plus A2 cos 2 omega t plus etc. Suppose the response is the following, this becomes A1 dash cosine omega t minus phi. Suppose it becomes A2 dash cosine 2 omega t minus 2 phi. Suppose that means that this is phi, this is 2 phi, that means that the phase lag for the first component, the phase lag for the second component is just twice that value, that means linearly increasing. Then if I put omega t minus phi is equal to some omega t prime, this becomes 2 omega t prime, and therefore, this becomes A1 dash cosine omega t prime plus A2 prime cosine 2 omega t prime. So, the shape is preserved because the two are the same. If you look at these two, the only difference is there is a small change in the amplitude, of course, anyway which it is a, if I choose the omega by omega n large enough, then this A1 dash will be very close to A1, A2 dash very close to A2, and you will also see that the phase is changing by exactly the same ratio as the frequency of these two components. Omega t, 2 omega t, it becomes minus phi minus 2 phi. So, this is an ideal case, there is no shape, no distortion, no shape change. That means we can say that the response is faithful. Now, what I would like to do is to find out whether what we have got here for these two components is either in agreement with this or not in agreement with this. That is all what we want to look at. So, if I want to do that, so let us look at the following. So, you just look at 2 pi t minus 2.554, this is 7 pi t minus 2.981. So, you just remember that. So, what is the ratio of the frequencies between these two? This is 2 pi 7 pi, it is a factor of 3.5. So, if this 2.554 changes by a factor of the same factor, then we would have no change of shape. Of course, 2.554, this is 2.981, I can always add a certain number of pi's to that. So, that is a trick which I am going to use. So, let us look at that. That means suppose I take 3.5 theta, where theta is equal to omega t minus phi, that means 2 pi t minus 2.554 if I take as omega is theta, like t prime, instead of that omega t prime equal to 3.5 theta is what I am writing, because this will become 3 times this portion, omega t prime will be here, this will become 3.5 times omega t prime. So, 3.5 theta will be nothing but 7 pi t, because that will give you 7 pi t for the next component, minus 3.5 into 2.554. So, that is the value, this will be 7 pi t minus 8.939. So, I can write it as 7 pi t minus 2.981 minus 2 pi plus 0.3252. Okay. So, I am rewriting in this particular form. So, if a certain multiples of pi are added here, it is not going to change the value, because every time it comes back to the same value. Therefore, essentially what is happening is there is a net phase difference. So, net phase change, there is a net phase change of 0.3252 radians between the two components, and therefore, we can conclude in this example that this is not going to not faithful to the input. And what I will do is I will go back to the response curve, and immediately you will see that it is in agreement with what we have already seen. So, if I look at the response curve, there is a factor of 3.5, omega by omega n is 2.5, 2.5 is somewhere here, 2.5 is somewhere here, and the second one is somewhere here. Therefore, you see that now it is quite departing from that. This is the difference we are talking about. If I had a case where it was 4 and let us say 3.5 times 4 will be 12 point whatever it is, 13.5, you will see that it would have followed faithfully, because it is in the linear part of the curve. So, in this case, because the first point is actually in the nonlinear part of the curve here, there is a net phase difference, that this is the phase difference we are talking about, that will correspond to 0.3252 radians. It will all be a plus, it will be a plus 0.3252 radians in the case, in the present case we have talked about. So, you see that the two things which we should do for vibration response, that is amplitude response, is to have omega by omega n large enough, so that the amplitude is more or less equal to 1. Secondly, we should choose that part of the curve where the phase change, phase difference between the input and output is proportional to the frequency. That means, I must be on the linear part of the curve to get a good faithful response for the vibration system, vibration measurement system. For the acceleration measurement, as you already seen, we should be in this part of the curve, so that you have a good faithful response with respect to the the acceleration response. So, we have some idea about the vibration transducers, and let me just look at one more which is very popular. It is called the piezoelectric accelerometer, and the principles are exactly like what we just now discussed. It consists of a seismic mass or a mass which is attached to a piezoceramic material, usually quartz, and this is a small thin layer of quartz material, and if the quartz material is subjected to an acceleration, so it develops, when you put a acceleration, it develops a charge across that. So, there is a charge is going to develop across the terminals. A terminal is at the top, another terminal at the bottom. You subject this piezoceramic material to a compression or a stress due to acceleration A, it will immediately give you a charge, and this charge will be appearing as a voltage. Actually, you can look at the following way. This piezoceramic is like a capacitance. The charge will appear, positive charge or negative charge will appear on one electrode, and the other electrode there will be a net charge of the capacitor, and therefore, this delta V is proportional to the charge which is generated, and this charge is proportional to the acceleration, and therefore, you can see that you are going to have a nice piezoelectric accelerometer having a good acceleration response. Again, the same principles which we had which we have just now enunciated are going to hold for this case also. Omega by omega n, large values is going to give you a good amplitude response, small values are going to give good acceleration response, and so on. And a typical shape of this transducer is shown here in the inset. roughly 16 millimeter diameter. This is a model made by Endevco, and the model reference number is given here, and I have in fact taken the picture from their website. This is from California, USA, that is the Endevco corporation. They make this transducer, and you can see what happens. Here you take the electrical output out. This is the inside this you have the seismic mass as well as the piezoelectric ceramic, and this is attached to the body whose vibration we want to study by using a suitable arrangement. So, let us quickly go through the principle of this particular sensor. We know that the capacitance is equal to a constant k times A divided by delta, where A is the cross sectional area and delta is the thickness of the piezoelectric, because it is just a dielectric constant, piezoelectric constant. So, Q is d into F, where F is the force and d is the dielectric constant for that particular material, and therefore, you can see that delta V is Q by C, the charge divided by C. So, charge divided by C, Q is equal to d into F, F is equal to m into A. So, I have taken F outside, d into m into A is dF, that kappa A by delta has come here, and you can see that delta V is proportional to acceleration, and this is the d delta m by kappa A is the sensitivity of the instrument. So, it is given by the seismic mass, the dielectric the piezoelectric constant, then the thickness and the area of the material and the dielectric constant of the thing. So, potential difference is proportional to the acceleration. So, sensitivity is defined as, for charge sensitivity is Q by A, where Q is the charge divided by the acceleration. Typical value is about 50 to 10 to the power of minus 12 coulomb per gram, per coulomb from G. G is the acceleration due to gravity, standard value. And voltage sensitivity is defined as delta V by A, and that is given by d delta by kappa A into m. So, these are the two things which we usually talk about. For example, I take a typical sensor made by Bruel and Kerr, 8200, this is the name of the product. It is useful for measuring forces between minus 1000, that means compressive, to tensile 5000 newtons. Charge sensitivity, that is what we just now discussed, 4 10 to the power of minus 2 coulomb per newton. Capacitance is about 25 10 to the power of minus 12 farad. Stiffness is 5 10 to the power of 8 newtons per meter. So, the material itself has got a stiffness, which is the spring is built into the system in that sense of the term. Resonance frequency with 5G load mounted on top is 35 kilohertz. So, see the advantage of this particular instrument, the frequency is very high, and therefore, it is very useful for measuring even very high frequency accelerations in this particular case. Effective seismic mass above the piezoelectric element up to 3 grams, below 18 grams, and the material of the piezoelectric material is quartz. Transducer is housed in a SS316 stainless steel, diameter is about 18 millimeter. The transducer is mounting is done by threaded spigot and tapped hole in the body. So, use is made of a charge amplifier. We will talk about that a little later when we talk about signal conditioning and so on, for signal conditioning. Useful frequency range up to 10 kilohertz. So, this is a very small instrument capable of being used for very high frequencies. So, I think we have just enough time to just look at a few things. We will come back in the next lecture. So, what we are going to do is look at some of the recent developments in this particular field. If you remember, when we were talking about the measurement of velocity of gases and so on, we were talking about the new non-invasive method of measurement. We talked about ultrasonic and then the laser Doppler instruments. So, the same principles are used also in the measurement of velocity, measurement of acceleration and measurement of displacement in a vibration system. So, a laser Doppler vibrometer is used in the measurement of either velocity or acceleration, as the case may be, in the case of vibratory systems, vibrating systems. So, we will look at the principle of operation of such, and then we will look at some of the details in the next lecture. So, I have taken this from a recent paper by Rothberg et al., and it is from Optics and Lasers in Engineering, it talks about the development of a Doppler accelerometer, and of course, it compares with laser Doppler velocimetry. We will not worry about the comparison, we are only interested in the development of the laser Doppler accelerometer itself. And let me just briefly see what it consists of. In the next lecture, we will be able to look at the things in more detail. So, we have a laser source, and then we have a beam splitter. Part of the beam is sacrificed, it goes away from the system, and part of it goes and hits the target. The target is the one which is going to be vibrating. So, we want to measure the vibration or the amplitude, either the amplitude, the velocity or the acceleration of the target, and this beam is going to hit the target and it is reflected back, retro reflected, and then the beam splitter will send part of it at 90 degrees to that, okay, and it will be incident on a second beam splitter and it will be reflected and it will go and fall on a mirror, and we have deliberately a long path which we call as path imbalance delta L. In the next lecture, we will of course find out why we have this path imbalance. So, the reflected light from here and the light which goes through, it comes back here, these two are going to combine together and are going to be falling on the photodetector. So, we have a reference beam, as you very well see, a reference beam and a beam which has, in fact, there are two beams now. One, both the beams have undergone some change because of the target is moving, and these two are combined at the photodetector, and the information we get at the photodetector will have some information about the acceleration of the target, as we will see in the next lecture. We will look at the principle of operation by actually looking at how these two are going to combine here, and what is that information which we are going to get, which is going to be proportional to the acceleration of the target. We will see in the next lecture. Thank you.